Lab 10 Alarm Clock Controller. The goal of this exercise is to create a simple FSM which will control the alarm clock. The alarm clock controller has three inputs: AL, which is the alarm mode. When pressed and held, the alarm clock shows the current alarm, and pressing HR or MN button will change the alarm. When released, the current time is displayed and HR or MN button will change the time. If HR is pressed and held, the R digits of the display shall increment. Similarly, if MN, that is minute set, is pressed and held, the minute digits of the display will increment. The state machine has 6 outputs with the following functionality. If show_t goes I, it selects the current time for the display driver and time set components, displaying the time and enabling the time for adjustment. If load_t goes high, it stores an adjusted time as the new time. If show_a goes I, it selects the alarm time for the display driver and the time set components, displaying the alarm and enabling the alarm for adjustment. If load_a goes I, it stores an adjusted alarm as the new alarm. If increment_hr goes I, it increments the R digits in the time set component. If inc_min increments, the minute digits in the time set component shall increment. The FSM is positive edge triggered here, and the reset is asynchronous and active low. From the diagram, we see that on reset, the controller is in the state show_time. While in this state, if AL goes low and HR goes high, the transition occurs to increment_TI_HR state. Else, if AL goes 0 and MN goes high, the transition occurs to increment_TI_min state. While in increment_TI_HR state, if HR goes 0, then the transition occurs to time_set state. Also, if in increment_TI_min state and MN goes 0, the transition occurs to time_set state, and the transition occurs to show_time in the next clock edge unconditionally. The value of the outputs in each of these states is shown in the output decode table. While in show_time state, the output show_t goes I and every other output is driven 0. While in increment_ti_hr state, the value of increment_r goes I and every other output is 0. While in increment_ti_min state, the value of increment_min is high and every other output is driven 0, and so on. Similarly, while in show_time state, if AL goes high, it goes to show_alarm state, and so on. You can have your own implementation of the alarm clock controller, but the one shown here is the simplest, safest, and easiest to test. We shall implement the FSM process structure shown here. We use a single register process for the next state and the state logic, and we use the concurrent statements to decode the output from the state. Let us code the design. Create the entity control and architecture RTL for the FSM in a file named control.vht. Declare an enumerated type for the controller states for better readability. The process FSM will implement the control FSM in accordance with the state diagram. We see that on reset, the state is assigned with show_time. Else, on rising edge of the clock, while in state show_time, if AL is high, the transition occurs to show_alarm. Else, if HR is high, then the transition occurs to increment T_HR. Else, if MN is high, the transition occurs to increment_TI_min state. Similarly, if the controller is in show_alarm state,
if AL is 0,
transition occurs to show_time. Else, if HR is high, the transition occurs to increment_AL_HR state. Else, if MN is high, the transition occurs to ink underscore al underscore min state, and so on. We derive the output depending upon the state values based on the output decode table shown on the right. From the decode table, we see that show underscore time is high only when the state is show underscore time, else it is 0 for every other state. Similarly, show underscore a is high only for the state show underscore alarm, and it is 0 for every other state. Similarly, increment R goes high when the state is increment underscore AL underscore HR or increment underscore TI underscore HR, and so on. Let us compile this file. Let us implement the test bench code. Create an entity tb underscore control in a file named t underscore control.vhd. Until now, we have only viewed the output graphically and verified. In this lab, we shall implement the checker logic to automatically compare the expected and the actual results. For this, the test bench uses a record type with the three elements: stim, which denotes the three FSM inputs AL, MN, HR, resp, which denotes the six FSM outputs, and the third field, string, containing the state name. We shall create an array of this record, one for each test pattern. We create a for loop to index through all the elements in the array. Stim is applied on the positive edge clock. The FSM output is compared to resp on negative clock edge. And the ESTR string is used in the report statement if resp and outputs do not match. Check that the test bench controller component declaration and instantiation matches your control entity. IO underscore vec is the record which holds the stimulus, expected results, and the error message. And IO underscore array underscore T is the array of records. Each element of this denotes one test pattern. The constant IO underscore array is of the type IO underscore array underscore T, which consists of the test patterns stored in the array of records, where each element denotes one test pattern. We see that the first 3 bits denotes the stimulus, the next 6 bits is for the response, and the next 9 bits are to display the error message. We see that from the state diagram, when AL, MN, HR are all zeros, the state is in show underscore time, hence the value of show underscore t should be high and every other output should be driven 0, and so on. We use this array of record to implement the checker logic. We instantiate the DAT and then generate the clock with time period of 10 nanoseconds. We apply the reset. We declare signal out vec in order to capture the output of FSM into a vector. This we will use while comparing with the expected results which are stored in the array of records. We index through every element of the array of records using a for loop to drive the stimulus and compare the output. We drive the stimulus on the negative edge of the clock, and hence we wait until clock equal to 0. The stim field of the record is assigned to the input signals AL, MN, and HR. We know that OutVec contains the captured values of the FSM outputs. We shall compare with this the response field of the record. We check the actual output with the expected output. We use the report statement to report the error. Integer tick image of I converts the value of integer I to the string type. Basically, here it denotes which test pattern it is referring to. Basically, the report statement here prints out the expected value and the actual value obtained. Output equal to 0 implies we have found no output. This is printed against the expected output. which is given by the string field of the record. Similarly, when outwake is 1, it implies increment underscore min is I, and so on. So the report statement will print out the test pattern number, expected output against the found output in a string format. Finally, we report simulation over message and then execute the wait statement to suspend the process. Let us execute the extend command and see the results in batch mode. We see that there are no errors reported. Let us purposefully induce an error and check the behavior. Go to file control.vht. While in show underscore alarm state, we know that if mn goes high, the transition should happen to state increment underscore al underscore min. Now let us change this intentionally to a different value, say increment underscore al underscore hr, and check the behavior. Now rerun the simulation. We see that an error is reported. Say for test 15, the expected output was supposed to be increment underscore min, as the state was supposed to be increment underscore al underscore min, but we have found the signal increment underscore r to be I instead. Let us undo this and introduce a bug in the output logic and observe the behavior. Say let us change the value of show underscore t to be 0 when the state is equal to show underscore time. Rerun the simulation. We see that an error message is reported. It says test 1 has failed and the expected output was supposed to be show underscore t, but we have found no output here as we changed the value to be 0.
Let us run the simulation in the interactive mode using -GUI option and observe the state transition happen in the waveform window. Select the signals from the controller level instead of the top TB level, unlike in other labs, in order to include the local state signals so as to observe the state transitions in the waveform window. Run the simulation, adjust the time scale and the zoom option. Let us change the color of the inputs. Let us change the color of the input signals for better visibility. At 10 nanoseconds, reset is active, hence the state is in show underscore time, driving a high on the output signal show underscore t. At 15 nanoseconds, AL is 0, HR is high, hence the state transits to increment TI-HR, driving a high on the signal increment hour. At 90 nanoseconds, HR goes low, hence the state transits to time underscore set, driving a high on the signal load underscore t. The state transits to show underscore time in the next clock cycle unconditionally, driving a high on the signal show underscore t. This illustrates the current time hour increment. At 130 nanoseconds, AL is 0, HR is 0 and MN goes high, hence the state transits to increment underscore TI underscore min. At 170 nanoseconds, AL, HR, MN are all zeros and hence the state transits to time underscore set, and in the next clock, the state transition happens to show underscore time, driving a high on the signal show underscore t. This illustrates the current time minute increment. At 210 nanoseconds, AL goes high, HR and MN are all zeros, hence the state transition happens to show underscore alarm. At 230 nanoseconds, AL is high and HR is also high, hence the state transits to increment underscore AL underscore HR. This drives a high on the signal increment hour. At 270 nanoseconds, AL is high, HR, MN are all zeros, and hence the state transition happens to alarm underscore set, driving a high on the signal load underscore A. The state transits to show underscore alarm unconditionally in the next clock cycle. At 310 nanoseconds, AL is high and MN is high. This transits the state to increment underscore AL underscore min, driving a high on the signal increment min. At 350 nanoseconds, AL is high and HR and MN goes low, hence the state transition happens to the state alarm underscore set. The state transits to show underscore alarm in the next clock unconditionally. This illustrates the alarm minute increment. This verifies the functionality of the alarm clock controller.
Now let us synthesize the design. Copy the genus shell script and change the design variable to control and execute the genus command to invoke the genus tool. View the schematic in the schematic pane. This completes this lab.